Hello there. This is a video talking about dealing with a free response problem involving charged particles. Here's the problem. Two oppositely charged particles are initially at rest at a distance of 2d away from each other. The first particle, Q1, has a charge half as large as the second particle, Q2, but possesses double its mass. Assume that the system only includes the two particles. Part A asks for you to derive an expression that can be used to determine the velocity of Q1. Part B states that after t equals 0 seconds, so essentially when the particle starts moving, student A states that since Q1 is more massive than Q2, the momentum of the system increases. Student B argues that the momentum of this system will remain constant. Explain who is correct and why. Part A, derive an expression for velocity. So if you need to, I would recommend you to, if you feel you need a better understanding of what's going on, I would recommend drawing a diagram for this problem. So here this diagram shows where the two particles are in relation to each other, as well as their charges. We got Q1. We have Q1 over here with one charge, and this Q2 with twice its charge at this distance. We can see that over here, this shows the forces that are being applied. This force going in this direction, showing the force that Q has onto 2Q. Like I say, it goes in this direction. The second force here shows the force that 2Q has on Q, which is in this direction. This represents the attractive forces between the two particles. Now, over here is just Q1, which is this particle, and it shows the direction in which it is attracted and essentially the direction in which it will move after t is equal to 0. So keep in mind that when I say we're talking about the velocity of Q1, we're really talking about the velocity, the final velocity of Q1 as, yeah, so this would be the opposite if we're talking about 2Q, where it would move in this direction. So since we're trying to find the velocity, we got to start somewhere. So I think best place to start, there are probably different ways to go about it, but the way that I'm going to go about it is we're going to start with the equation for finding the force of the electric fields. And this is the force of the electric field on a particle is equal to the Coulomb's law constant times the particle, the point charge is what it's called, times the other particle, all divided by r squared. R is the distance, and here the distance is 2d, so we just plug that in here. Also, keep in mind that force is equal to mass times acceleration. So that allows us to substitute this equation for F and set the mass times acceleration equal to it. And with this, we can find the acceleration. And if we know the acceleration of a particle, as represented here, we can plug it into the kinematic equation dealing with acceleration, time, and the velocities, and we can plug it in here. And this will give us the equation for the final velocity of Q1. Excuse me. What this is essentially saying that the final velocity is equal to the initial velocity plus time times the force of the electric field divided by mass. So B asks to figure out which student is correct and why. So I'm going to put all of this here first and paraphrase what exactly is going on. So we have to keep in mind that the law of conservation of momentum states that a system's momentum will be conserved unless there's an outside factor that affects it. And since we assume that the system are the two particles together, then if we're talking about the momentum of the system, then we're talking about both particles combined. So therefore, since A is talking about one of the charges being more massive, you're turning that one charge into its own system. So therefore, he's already incorrect. So student B is correct just because of that fact, but I want to go more in depth into this. So the momentum of each particle, as momentum is a component of the force a particle experiences times the time, then since they're both experiencing the same force and it's happening at the same time, then their momentum is equal. But because they're at opposite ends, they're going in different directions, then they're equal and opposite. Since the net momentum is equal to, the sum of the total momentum of the system, then that means since they're equal and opposite, the net momentum is zero. And even when they stop, since they're not moving with each other, the net momentum is still zero because momentum is a component of is the amount of force experienced. Is essentially what keeps them moving. And since they're not moving, once they collide and stick to each other, as particles do, if they're attracted, their net momentum will be zero regardless. So yeah. Thank you all for watching. I hope this was helpful in figuring out helpful for you all. Like, comment, subscribe. Although probably only Rockland High students would see this, but that's it. Doesn't matter. Thank you again. I'll see you in the next one.